Swayam Prabha. Digital India. Educated India.
Welcome back. In the previous video, we saw some variations of the RNN structure using GRUs, the gated recurrent unit. GRU of course is a recent version, 2014, and we saw that by introducing new weights and a slightly more complicated structure, we could probably handle the vanishing gradient issue. So, GRU of course was not the first architecture to handle this. The oldest architecture to do that was LSTM in 1997, okay, and this is still the industry standard in many ways, though as you will see the structure is slightly more, a bit more complicated than GRU, but not by very much. If you got the ideas in the previous video, the LSTM idea should also be fairly clear. So, what is LSTM? LSTM stands for, as I had said in the last video, long short term memory. So, remember the short term sits together and LSTM was the first architecture to use the idea of a separate memory cell. Okay. So, when we were dealing with GRU or the simplified GRU, we had something like HT is f times HT minus 1 plus let us say 1 minus f times G, where G was the output of the vanilla RNN. And the idea there was to retain some portions of your old calculations into the new ones. In the case of LSTM, we will be actually using a separate cell altogether. This is a memory cell. So, heuristically this is sort of like having some numbers, you retain it in a separate memory bank and while you are calculating with some other numbers. So, I will just show you the formulation. So, we write CT, notice the analogy with what we had before is f times, this is once again the Hadamard product or the element wise multiplication product, f times CT minus 1 plus I times G, where I is now called the input gate, f is like last time it is called the forget gate. So, the ideas are very similar. Once again we want f to belong to 0 1, similarly I should also belong to 0 1, but this gives you only CT. What happens to H? H is the output that we are actually interested in. H is now given as O times tan H of CT, okay. And O once again is another valve or another gate which also belongs to 0 1 and it is called the output gate. Okay. So, now we have 3 gates F, I, O and we also have to predict G. Okay. So, just to write a summary of how we calculate LSTM. LSTM is calculated as HT is O times tan H of or some other nonlinearity of CT, where C is the memory, and CT itself is calculated as f times CT minus 1 plus I times G. And now all these parameters need some definitions, and these definitions you could probably write down intuitively even before I do, and I would recommend that maybe you pause the video and try it once just to make sure that you have understood things, but I will quickly write them down in a second. So, these ideas are very similar to the ones we had used in simplified GRU and even in GRU. So, the idea is simple. Since O has to belong to 0 1, you say O is sigmoid of some ZO, where Z will be a linear combination of what came in. Similarly, F will be sigmoid of ZF. Similarly, I, the input gate, will be sigmoid of some ZI, and G being the output of a vanilla RNN is simply tan H of ZG. Okay. Now, what are these ZO, ZF, ZI, ZG? We can write them down pretty easily. ZO will be WO HT minus 1 plus UO XT. Similarly, ZF will be WF HT minus 1 plus UF XT. ZI is WI HT minus 1 plus UI XT, and finally, ZG is WG HT minus 1 plus UG XT. All these put together give you LSTM. Now, if you see LSTM, it has how many unknowns? You know, whatever be the size of the W matrices, you have 8 unknown weight matrices. Just for comparison, plain vanilla RNN just has 2 weight matrices. Now, if you recall, when we were doing back propagation through time, we had to find out both these weight matrices, including of course, the output matrix. I have not talked about that here, okay. But if you have outputs, you have to find out back propagation for that, though the output matrix back prop, as you had seen in the back propagation through time, was straightforward. Now, if you use all these 8, you will have to do back propagation for all 8 of these matrices. So, that is what will change, and if you use simplified GRU, we saw that there were 6 matrices, etc. Okay, and sorry, simplified GRU had 4 and GRU had 6 matrices. So, it is just a question of how much expenditure you are willing to bear. Now, LSTM typically can train or can retain non-vanishing gradients for greater number of layers compared to GRU, and GRU typically can retain greater number of layers compared to vanilla RNN. Okay. So, this is remember, when I say LSTM greater, what it means is the number of layers that you can train with LSTM, the depth of the architecture can be greater with LSTM compared to GRU, and that compared to vanilla RNN, and you have to balance it against typically the number of weights that you have to train. So, of course, this is also true of non-vanishing layers that you can train plus time taken for computation. So, LSTM will typically be more difficult to train in terms of computational time, it will take greater time for you to train, and it will also take you slightly more time to run because it has more matrices in there. So, everything is greater about LSTM. Now, typically a rule of thumb that is suggested, at least in modern days meaning just as of 4 years, is that you try vanilla RNN on a task, and if it is a small number of layers, if that works well enough, good. Otherwise, try GRU on a task, and if that works well enough, good. If not, then try LSTM. Okay. Of course, depending on what people's priority are, many people typically tend to use LSTM off the bat. Okay. So, that is certainly a possibility. Now, just to repeat the exercise that we did with GRU and simplified GRU, I will also draw sort of the diagram for LSTM. Remember now that we have not only HT and XT coming in into this box, which is finally going to spit out, oh sorry, this should be HT minus 1, then HT comes out, but not only that, you also have your memory cell or memory computation. So, we also have CT minus 1 coming in and CT going out and so on and so forth. Okay. So, CT progresses, HT progresses, and there is some processing that happens inside, which was given by our formulation above. Now, what was that? HT minus 1 and XT combine as usual to give our vanilla RNN output. Now, CT minus 1, if you remember, there is a valve here, it looks like infinity, but it is actually a valve. So, I gets multiplied by G, the forget gate gets multiplied by CT, the two combine, and this is what gives us CTS output. At the same time, the same CT comes down here, okay. You run it through a tan H, run it through the output gate, and what you get is HT. So, this is a simple schematic of LSTM. Now, this can be shown in many different complex ways, but I like this because this kind of tells you what the mathematics is doing sort of in a simple way. You can also see several versions of this online, each person has their own diagram of LSTM, GRU, etc. I prefer this, you do not really have to learn it, it is for those people who prefer visualizations to arithmetic or algebraic formulae. So, LSTM is the industry standard for RNNs. You can blindly use LSTM more or less today for any RNN task that you see fit. A warning is that it takes a long time to train for many most of the language tasks that we are interested in. Thank you.